All right. Well, anyway, so like I said, if you are helping me move the stuff tomorrow, meet by the Circle Drive at 4:30. I would expect we're going to be out of the place by about 4:45, 5. Then it's about a 30-minute drive back to my house, or however long it takes to get loaded, maybe 30 minutes. So we'll probably be back at my house at 6.
I just meet at your house. Wait, are you coming from the school to your house?
No, school to the place, back to my house.
I was thinking save myself driving because I got out of class at 2.
Actually, let me think about that. You actually probably could meet at my house because I think we're going to have to go by my house to get there.
Okay.
So if it's more convenient to meet at my house, then if you know where my house is, if you're in the Grafton area, meet at my house.
So I look like 5 minutes.
At 4:40 at my house.
All right.
So I figure we'll probably be eating around 6:30. That's the goal, or possibly visiting the emergency room. One of the tomato, or whatever. Does anybody actually call potatoes potatoes? Never heard that. That's like part of the joke, though, right?
Yeah. I don't even know where that came from.
It's dumb.
Stupid people want to be different.
Good call. Okay, so let's talk about the midterm, and then I'll take any questions you have on that, and we'll review. So midterm will be this Thursday, immediately following the computer science get-together. Computer science get-together is at, what, is it at 11:30? 11:30 to 12:30, I think, down the hall. Confirm. Somebody confirm.
Yes.
Sound right? Perfect. So it's confirmed. Yeah, so on Thursday, I think it's at 11:30. The computer science get-together is down the hall. And that other room is going to be food. We usually do pizza and Quiznos. I can't absolutely confirm that, but that's typically what it is. Pizza and Quiznos or pizza and Subway. We might alternate, but pizza and sandwiches. I would encourage you to get there early if you've never been to one of these things. They're pretty cool events. The cool part is there's lots of good prizes. So apparently I heard there's an iPad Air this year. Is that a true statement?
Is it Air Mini?
I heard iPad Air, but I don't know. I didn't read it, I heard. Mini? iPad Mini? Well, whatever. There's an iPad. But in any case, if you want to have first dibs on the good prizes, what you do is you show up at, be there before 11:30 or right at 11:30 when we do that meet and greet thing, where it's like a piece of paper you run around. You have to get, people's signatures, who has the same shoe size as you, and who uses the same amount of toilet paper, that kind of stuff. Single ply versus, yeah, or quad ply.
Kind of the strong stuff.
So in any case, the best way to get the best prizes are to win either the one where you get all the asterisks filled in first, or the one where you get the full sheet filled in first. Those are the people who get the first dibs on the good prizes. There's plenty of decent prizes. So after that, then there's like quiz questions. So we put up, on the overhead projector a bunch of questions, and whoever raises their hand first and gets it right, then that's the next person who gets the prize. But there's usually some pretty good stuff. I know Dr. Locklear is actually going to make an appearance. He is on sabbatical this semester, but he's going to come in for that. So if you miss him, you can come and say hi to Dr. Locklear. And let's see, Professor Wall will not be there. His wife is having a procedure done. So you'll have to deal with me and Dr. Locklear and the other crappy faculty, whatever. Whoever.
First thought that Locklear wasn't going to be there either, so it's just going to be run solely by you.
Well, that wouldn't have happened. No, I'm pretty sure if that was what was going down, he would have just had Valerie Locklear run it. Like if given the choice between me running it and his daughter running it, he would have just chosen his daughter. What's this?
What would have happened if you
I just wouldn't have run it. No, this is all a true story.
What would you do?
With him being on sabbatical this year, since I technically have seniority, I've been here significantly longer than Professor Wall. Dr. Locklear came to me to determine if I wanted to be like the interim chair in the meantime while he was gone, like the representative for. I mean, I think we both knew where it was going. He kind of like, yeah, do you want to be the chair since you've been here longer? It's going to be a lot of work. I said, well, I'm willing to do it, but why don't you ask Bob?
And we're willing to do it. Just put
Hopefully Bob says yes. So what I am officially doing right here is I'm putting a plug. Whenever Dr. Lackley retires, Professor Wall, I'm encouraging him to be the department chair. That would be very bad for the department if they had anything involving paperwork or things that are due on time. Yeah, that's problematic. Yeah.
So what you're saying is that like leading the get together would have been just like, all right, is everyone here?
Go. Are the pizzas here yet? Eat. Now get out.
Prizes are
Exactly. Just get in line, pick a prize.
First one, make the coolest weapon and use it on someone.
That happens to me every single. Actually, at least I'm given a midterm after this year. Previously, he always gives out these like Nerf weapons and the flying helicopters and stuff of that. So the whole next class, I'm like dealing with students dive bombing me and stuff. It's terrible. Yeah, even just this semester, I finally finished designing one of our grad classes that was assigned to me 4 years ago. I think 4 years ago. And there was a 1 month time frame, 4 years ago. I finished it at the beginning of the semester. A little late. Hey, they still paid me. But yeah, so if ever given the option, vote Professor Wall to department chair. I don't want it. Okay, so let's talk about the midterm. Midterm will be Thursday following the CS get-together, which I do encourage you to go to. I'm going to design the exam to take about 45 minutes, assuming you know your stuff, you're competent. You will have the entire hour and 15 minutes to do it. It'll be a short answer essay. There may be some programming on it. I would say it's probably not going to be really programming centric. But programming would be fair game. I would say there's going to be a lot of conversion stuff and things like that on it. If you were comfortable with that last homework assignment, kind of the long homework assignment, I would say that would be very good preparation for the midterm. I think the exam will pull from that pretty heavily, and then some older stuff. But I think those are the types of questions you might be dealing with. So let's go over some of the topics, and if you want me to cover any of them or recover any of them in any sort of depth, I'm happy to do that. And then you can ask any questions about preparation, blah, blah, blah. So I'll just talk about each one at the high level, then you can ask questions. So hardware versus software. So this is the idea of us writing software as opposed to engineers kind of building the hardware, how they're both kind of programming-esque type of activities, and then where those two get married together. Analog versus digital, representing those signals, so representing digital and analog signals using binary. Frequency versus period. So period is how often something happens, right? Yay, nay. That's frequency. So what's period? How long it occurs for. Each time it zaps, how long it's there for. Make sense? Duty cycle, that's how long it's on that's the period of an on position. Period of a true.
The amount of time it takes where you need to go.
Yeah, it's the same thing. Isn't that saying the same thing?
I guess so.
Knowing all the time prefixes, nano, micro, all those things. A fair question might be me giving you a crazy number and saying, write this in the most efficient way. Something like that with one of the prefixes. Let's see. Converting between bases, decimal, octal, binary, hex. All those are fair game. I would think that I would mostly focus on decimal, binary, and hex. But I would say it's very likely I will put a question on there dealing with another base, whether it's octal or me just making up a base like, base 19 or something like that. Well, no, I want you to show your work. But kind of the idea being that you're proving to me that you understand that converting between bases is an algorithm-based thing that's always the same. That make sense? Very likely I'm going to ask you to do our quick convert hex with hex to binary with nibbles and binary to hex with nibbles. Let's see. So using a various number bases, the idea of nibbles, bytes, words, double words, really words and double words we didn't deal with, so maybe just know the existence of those. Maybe I ask you to define these four. So a nibble is 4 bits, a byte is 8 bits, a word is 16 bits, and a double word is 32 bits. Let's see. Sampling theory, kind of the idea of reading from a signal, reading from a digital signal. Well, I guess it would be an analog signal, but we're reading it. So sampling would be how often do we grab that signal? And we want to sample at least as often as the frequency, but realistically, we probably want to do some multiple of that so we don't miss data in the middle, right? So questions involving that would be fair game. LCD screen resolution versus DPI. So the idea of how kind of pixels on any sort of screen, really. We talked about it in terms of smartphones, but the same thing would go for anything else. Smartphones just kind of fit our worldview and technology today. Doing math with binary numbers, doing math with hexadecimal numbers, and that was your assignment for today, right? Finish it, write the hex version of that. Okay, so we'll look at that here when we're done with this. Binary coded decimal. So being able to work with that and understanding the difference between that and, well, I say understanding the difference between that and hex representation, but really binary coded decimal allows us to represent things as zeros and ones, but it's not necessarily mathable, right? Unless we're dealing with powers of 10. So it's more of a data representation language, almost the JSON or the XML of the binary world, if you want to think about it that way. So again, binary coded decimal, and then gray code, specifically dealing with the what was it, a rotating shaft? Is that the?
I recall something to the head.
I recall something. Okay, so gray codes. Potentially, I'll have you give the all the gray codes for a small number of bits, maybe a 2 or 3 bit gray code chart, something like that. I wouldn't ask you to do anything bigger than 3 bits. In fact, I would probably say 2 bits would be fair. Remember in the homework assignment, you had to generate all the 5-bit gray codes. It becomes a little verbose, right? I don't know that I want you spending 25 minutes on one question just repeating the same crap over and over again. So I might even ask just generate the first 5 gray code values for, even if I chose a 6-bit number or something like that. Generate just the first 5. Something along those lines would be fair game. Okay, so questions on any of the topics dealing with the midterm? Need me to go over any of these things? Review any of this stuff? Go ahead. Sure. So kind of at the high level, and here I'll bring up the slide set, should be fairly early on. So at the high level, analog is what we consider to be the real world. So it's a bunch of floating point values with infinite precision. So if we're taking the temperature outside, we typically as humans think, oh, it's 67 outside or it's 63, but really we can measure the actual temperature outside to an infinite number of decimal places, right? So analog, when we think about that signal, we think about a big old wave, okay? So there's literally an infinite number of values between 50 degrees and 60 degrees because we can account for every single little decimal point. And we talked about it in terms of kind of television. If you are used to if you ever had rabbit ears in your TV, there was a such thing as sort of kind of having a picture, right? You might be able to watch the football game. It was fuzzy, but you can kind of make out stuff. Where with our modern day digital television, it was either on or off, right? You don't get that. Oh, the picture's either basically perfect or the picture's completely off. Digital signals, this is our computer world. So we have either something is on or something is off. So if we're looking at the signal for that, it's very much kind of a square looking thing. Now what becomes interesting, and that's on the thing here, I think representing digital and analog signals in binary, we need to choose how many decimal places we're going to support. So for instance, let's say we're doing temperature and we want to, we want to be able to represent the temperature to a half a degree, something like that. Analog, we can represent the temperature to an infinite number of places, but maybe we want to only do one decimal place to 0.5, up within a half a degree. We can then choose those are our increments. So if the smallest temperature we're going to support is -50, and the hottest temperature we're going to support is 120, we just need to be able to support -50, -49.5, -49, so on and so forth. So we got to figure out how many increments do we have there, and then we can use an appropriate size binary number that is capable of representing all those increments. That makes sense? So if we say, what did I say, 120? -50 to 120. So -120 minus, 120 plus 50 is 170 times 2. So,
You have to put the one.
yeah, I get it. All right, so it's 170. So it's 340, right? So 340, we have 340 increments. So how many bits do we need to support those increments? Well, 8 bits lets us do what? 256 unique values. So we need more than that. What does 9 bits let us do? $512? Yeah, just double it. So really we can represent all of those values for our, all the values for our temperature with a 9-bit binary representation for each of those jumps.
Wouldn't you have to use a 10-bit because it's a sign because you're going into the negative?
You could. Yeah, it really depends on that, because keep in mind that you're using the binary number as a representation. The binary number doesn't actually become the real value. You're not storing the real value in there. You're storing the number of increments that you're going to have. So depending on how you wanted to do it, you actually could probably... For that type of application, you could use a 10-bit signed binary number. Actually, you couldn't. Because using a 10-bit signed binary number, you'd still only be able to hold the whole values. So you would use a 9-bit binary value to represent the 340 unique things you had. So the legal numbers that you would support would be 0 to 349. Where 0 is -50. 1 was -49.5, so on and so forth. Does that make sense? So that would be representing a digital signal with a binary value. Figuring out how many increments you're going to have and dividing it out. Okay, so does that kind of make sense? Analog versus digital? Or do you have more? Like, that did it? Okay. What else? So maybe even thrown in that same conversation, if I were to ask what's the advantage of an analog signal over digital, what might you say? We like digital because all our computers work in digital, right? But right off the bat, what's the disadvantage of digital?
Hard for us to read. Somewhat. I mean, it's not as...
Well, actually, can't we flip that over right away? Which would you prefer to read, an analog clock or a digital watch? I mean, digital is easier to read, right? I mean, some people are really good at reading analog clocks, but everybody's good at reading a digital clock, right?
Let's put it in military time now.
Military time. What's the downside of digital? It's got all sorts of positives, I get it. But
Is that you miss things in between?
yeah, precision. Yeah, we give up precision the second you move out of analog. Analog literally has infinite precision. So that's great if you need to be precise. But does infinite precision really make sense in the world? It's infinite. You know, even when we're dealing with machining parts and stuff like that, you know, parts are machined down to a certain threshold. You know, it might be in terms of microns, you know, something really, 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 really tiny, but it's still not infinite. You know, it wouldn't make no sense, correct? But analog does allow us to represent infinite precision if we chose to, or a lot of precision at least. Where digital really locks us into having gaps in our amount of precision. And those gaps, the size of those gaps really turns into the problem we're grappling with over on the hardware side of how many bits do we use to represent a value. The more bits, the more precision, but the more bits, the more memory. That makes sense? Kind of becomes an interesting problem. All right, other questions? Go ahead. Gray codes? Okay. There you go, Abe. just don't break eye contact. Okay, so kind of the idea here. So actually looking at this value, is this the gray code value? It's not. So if we're looking at something like this, where we're trying to read which position a wheel is in, okay? Given this example, we call it the rotating shaft, and that becomes funny, haha. But really, we're looking at a wheel, and we want to know what position this wheel's in. And if we use normal binary counting, this is 0, this is 1, this is 2, this is 3, so on and so forth, right? The problem with this is we're going to have some sort of sensor out over here that's going to be reading from that number, reading from that value. And since these values, so we have a change from 000 to 001, we have one bit that changes. 010 to 001, we have how many bits that change? This bit changes to a 0, this bit changes to a 1. We actually have 2 bits that change, so on and so forth. So you start running into a problem if you use normal counting, where the number of bits that change between the steps is more than 1, giving you a gap for misreading it. So your sensor, depending on its frequency, depending on how often it's sampling, and even if it's sampling very often, might catch it in the middle of 2 numbers and miss a bit and actually read the wrong input. So what we do to fix this is we introduce this idea of gray codes. Mathematically, gray codes don't make sense in counting. But if we use gray codes to represent 5 or 6 or 7 things in a row, we can say, okay, well, here's the first gray code, here's the second, here's the third, and the difference between those gray codes is never more than 1 bit. Does that make sense? So we really are using them as a mapping. So an alternate counting sequence, only 1 bit changes between values. So here's your, we might have a sequence 000, 001, 011, so we only changed 1 bit there. Correct? 010 only changed 1 bit. 110 only changed 1 bit, so on and so forth. This isn't counting in normal binary. It's counting using gray codes. So this is not mathematically correct, but Abe, as the shaft turns, only 1 bit will change. So we do have an algorithm for dealing with this. So here's the algorithm for that. If you notice, we have this little kind of a picture down here. We add 1 bit over to the far left of your original value. And that creates a whole bunch of these kind of dividers. So we have a divider between these two numbers. We have a divider between these two numbers. We have a divider between these two numbers, so on and so forth. Okay, so we're going to add a 0 to the left side of the unsigned binary, our value, that we want to convert into gray code. There should now be n boundaries between the n plus 1 bits. So that's what all these boundaries are from. Notice we have this brand new boundary that was formed from the final 0 that we tacked on. Then for each boundary, we're going to write a 0 if the adjacent bits are the same. So in this case, 1 and 1 are the same bit. So we're going to mark a 0 down for our gray code. 0 and 1 are different, so we're going to record a 1. 0 and 0 are the same, so we'll record a 0. 0 and 0 are the same, we'll record a 0. 0 and 1, different, record a 1. 1 and 0, different, record a 1. So that's how we map a normal unsigned binary number to its gray code equivalent. That make sense? Using that algorithm. And by doing that, now we've guaranteed if we map, if we map 0, let's just use 3 bits as the example. If we map 0, 0, 0 to its gray value, the gray value is actually 0, 0, 0. If we map 0, 0, 1, it's also 0, 0, 1. But now as you start getting to the larger numbers, the gray code value may not be the same as the unsigned binary value. But what is guaranteed is that gray code value, between two gray code values, you have at most 1 bit. Well, you have exactly 1 bit that changes. And the reason for that is to handle situations like this, where you might have a sensor reading from the position of something to make sure that no more than 1 part changes between samplings. Make sense? So that's kind of the deal. And as I said, a reasonable question might be, generate the first 5, 6-bit gray codes, something like that. So you would take 0, 0, 0, 0, 0, 0, tack a 0 on the front of it, come up with that gray code, so on and so forth. So the first 5 would actually be pretty easy because really you're only doing like 3. Because the first 2 should be the same. Always in gray codes. That makes sense? All right, other questions? Go ahead.
The binary map.
Okay. So that's the stuff we've been talking about more recently, and for your homework you were supposed to do hexadecimal math. So let's jump down here. Surely I made a picture, didn't I? We did not do complements yet, right?
I think you kept deleting the pictures.
We kept what?
I think you kept deleting the pictures once you were done with them.
Oh, did I?
Maybe.
Oh, here's one. So, well, that's subtraction now. We don't want subtraction. Aha! All right, so if we have 2 numbers, just like here, let's start off with this example. Because really what we want to do is, let's say we're adding 10. Actually, let's say we're adding 17 to 25 in decimal. All right? So when we're doing something like this, here's our answer will be down here. We're going to take 7 plus 5. And what's 7 plus 5? It's 12, right? So what are we going to do? We're going to record the 2 down here. And we're going to carry the 1. Does that make sense? Now this is 1 tens place. Then we're going to say 2 plus 1 is 3, plus 1 is 4. So that's how we add decimal, right? And you've been doing that for years. adding binary is literally identical. Literally identical. The reason it seems more difficult is because we're not used to dealing with zeros and ones. So, for example, 1 plus 0 is what? That's 1. 1 with, and we're not going to carry anything, correct? 1 plus 1. That's 2. So how do I, 2 is not a legal binary number, right? So 1 plus 1 is what? 0, carry a 1. Because that's 1, 2 for base 2. So we're going to have a 0 here. And we'll carry the 1. So 1 plus 1 is 2. How many times does 2 go into 2? 1 time. That's our carry. Remainder 0. 0 plus 0 is 0, plus 1 is 1. So that's 1 with no carry. 1 plus 1 is, already seen this before, well, 1 plus 1 is 2. How many times does 2 go into 2? 1 time. So we will carry the 1. We'll record the 0. Then 1 plus 0, 0 is 1. So there's our final answer. So the math is literally identical to how we did decimal math. We just had to think about the values. And just to kind of show that over here, when we said 7 plus 5 is 12, how many times does 12, or how many times does 10 go into 12? 2 times?
Once with the remainder.
1 time with a remainder of 2. Exact same thing we did over here. So here's your quotient, here's your remainder. Make sense? So 7 plus 5 is 12. 12 divided by 10 is 1. Remainder 2. Just like saying 1 plus 1 is 2. 2 divided by 2 is 1. Remainder 0. See the pattern there? And we could take it one step further, just as a precursor to our assignment for today. I can say I have AB, and I'm adding to that 14. So this is going to be hex math. Well, B plus 4 is what? Okay, B is 11, plus 4 is 15. 15 is F. So how many times does 16 go into 15? 0 times. So no carry. Remainder 15, which is F. So it's always consistent, right? We can always do that math. How many times does 16 go into something? You know, we wouldn't, if we had 7 plus 1 over here, 7 plus 1 is 8. We can say how many times does 10 go into 8? Goes in 0 times with remainder 8. Okay? So B plus 4 is 15. 16 goes into 15 0 times, so we have no carry, with remainder 15, and 15 is an F. A plus 1. A is 10. Plus 1 is 11. How many times does 16 go into 11? 0 times with remainder B. Make sense? So the exact same algorithm, the exact same pattern, regardless of whether we're adding decimal, adding binary, or adding hex. Does that make sense? Okay. And you'll definitely have ones like that to do, and I want you to show your work. All right, other questions?
Use of octal.
Okay, use of octal. That's going to be a tough one. Can we come up with a valid use of that? That doesn't mean that I won't ask it. Is there a valid use for octal?
The only thing I had in my notes was nobody.
Yeah, I mean, I'm sure somebody has used octal for a reasonable purpose. It really comes down to, we can kind of sort of answer that by thinking about why do we use decimal, why do we use hex, why do we use binary? We use binary because digital is on or off, so we kind of have a necessity for a base that deals with that has just two legal digits. We use decimal because we have 10 fingers. So that base 10 kind of works for us. Right? But what if we had 8 fingers? Aren't the gray aliens supposed to have 8 fingers? Isn't that the rumor? The guys with the big bug eyes. Don't they call them the grays? I read a lot of sci-fi. Isn't that what they're called? Okay, fine. There's going to be aliens on the test now too. I think they're supposed to. I think all the reports of people who've been abducted and stuff say that they noticed they only had 4 fingers per hand. So maybe they would count in base 8. So correct answer is aliens. That's the correct answer. But you kind of get the point. Whatever's convenient for what we're doing. Like, why did we pick hexadecimal for memory? Is there anything special about that 16? Okay, so bases larger than base 10 can allow us to hold numbers in smaller footprints, right? But is there anything specifically special about hexadecimal? Why did we pick that?
It worked well with binary.
Huh?
It worked well with binary.
Okay, why?
Because the 0 through F fits into a
Nibble. So hexadecimal became very convenient because we can represent it using each character, each digit of the hexadecimal number system can be represented as a nibble, a 4-bit number. So that's why hex became, kind of a standard, because we can move between hex and binary very easily. That make sense? Now, are we going to eventually get to a point where hexadecimal may not cut it? I mean, we're not there yet. But certainly, we just keep fast forwarding into the future. We might get to the point where a base 16 number isn't going to be enough. So what do we do? What's next on the agenda? Go to a base 32. Base 32s we can represent with a 5-bit number. We're going to have to come up with a way to, a new name for that. It's not a nibble, it's a something else. It's a goat. Make sense? So, I'm not sure other than aliens that octal has a real great answer. Really, for any base, it's kind of picking a reason for using those numbers. Maybe it has to do with, binary makes a lot of sense. Decimal makes a lot of sense. Hexadecimal makes pretty good sense given this idea of a nibble and easily being able to go back and forth between binary and hex. And at the same time, it also gives us the advantage of being able to represent large numbers in smaller footprints. So it's kind of that compatible larger base that works well with binary and lets us solve the problem of representing things in smaller footprints. Octal is more of something that is a common base that's used for converting, and I'm sure there's some reasonable examples. I just can't come up with any off the top of my head. But so it fits into that category of bases that people have used, as opposed to like base 3 or something like that. But we've seen in here that all the bases are the same. Converting between them are identical. We only run into problems once we get bigger than base 36, because we run out of letters. I suppose what we can do is for bases bigger than 36, we can convert to a Unicode mapping system where we represent, instead of starting with A, the very first, a 10 is represented by a whatever the very first character in Unicode is. Let's just assume it's a question mark. I don't think it is, but let's just assume that's what it is. So then you have 65,535 unique characters instead of
We run out of that.
36. All right, other questions? Going once. Going twice. All right, let's look at our homework then. Okay, so we already did add binary numbers, 1011 and 1010. So let's look at the add binary. So this took in a binary 1 and a binary 2. We figured out what was the maximum length of either one of those so we can pad the other one, right? To make sure after these two lines, B1 and B2 both had the same number of characters in it, same number of bits. All right, then we keep track of a single overflow bit. So if we kind of translate that back to here, this was an overflow bit right here. Then this was that overflow bit. So we used only one number to represent that bit, one bit to represent all of our carries. Does that make sense? Because once we did this math here, we don't care about this carry bit anymore. We're going to reserve it for later on. So after we've done this math, we probably want to set it to 0. Because more than likely, when you implement this, you're probably always adding the carry bit in there, which I think we do in our algorithm. So you don't want to accidentally add a 1 just because the previous carry bit was a 1. So that's where our overflow comes from. Here's our answer we're going to be building up. So we're going to go through every character in one of our two strings, B1, B2. We know they're the same length right now, correct? That's where we guaranteed they were the same length up there. So we're going to go through, doesn't matter which of the two. We're going to go through the same number of times. We're going to store inside of an integer, temp, whatever our overflow currently is, would start off as a 0. So whenever we do math, the very first time through, carry bit's nothing, correct? Overflow bit's nothing. So temp will equal whatever overflow currently is, plus the integer version of the last character in B1. We're starting at the end of those strings. That is, we're starting over here, and then moving to here, moving towards the beginning. So the integer version of that, plus the integer version of the other thing. That's temp. Then, we're calculating our overflow. Our overflow is going to be whatever temp currently is, the sum of all that stuff, divided by 2. All right, so it's the whole number part. Then our answer is temp mod 2, the remainder, concatenated with whatever our answer used to be. Is that phone or laptop?
My phone.
Oh, your phone? Sometimes I do that in church by accident.
Why you feeling zombies?
Huh?
Why
I've been playing golf in church lately.
you practicing the swing? Practicing your swing?
There's a good game called World Golf Tour. Pretty realistic. Plus on the new iPhone 6 Plus screen. It's pretty legit. I don't have to bring my iPad with me anymore. It's harder to hide your iPad when you're at church.
You got big pockets, at least
Huh?
you can smuggle it in real well. You just gotta get the iPad mini.
No. I don't worry about smuggling it. I'm thinking more just when I'm sitting there.
Get an iPad
You
mini.
can kind of inconspicuously mess with the, a phone. It's actually a reasonable reason to, kind of the headache I run into at church is I go to a LCMS church, Beautiful Savior in Mequon, and there's a lot of standing and sitting. So every single time you stand up, you're going to put your phone in your pocket because you don't want everybody else around you to know you're still playing golf, and it would just be bad if you're standing there playing golf while you're standing up, and you're supposed to be saying the stuff, right? Yeah, so I play the golf during the hymns and the sermon if it's boring.
So they gotta make it where you can get Google Glass. It's all on it.
Google Glass has like 30-second battery life.
Yeah.
It's like, okay, go.
Well, and it turns off every 10 seconds.
I know, it's terrible.
So you're sitting there going like this. Turn back on.
Okay, so then at the very, very, very end, we tack on our overflow bit, whatever its final value is. That make sense? Okay, so it might be 0, it might be something, it might be a 1 in this case, but we'll tack it on in either case. So worst case is we have an extra leading 0 in our answer, still accurate. And then we'll return the answer. So that's add binary numbers. So you were supposed to write add hex. Add hex is going to take in our two numbers, still call them B1, B2, you can change them if you want. We get the number of bits, the maximum number of the two of them. We make sure we pad them out so they're the correct length. Then we have our overflow. Overflow is always going to be a number between what? I think I asked this question last time, didn't I? What's the overflow going to be? What's the biggest number we can have adding a single hexadecimal digit to another single hexadecimal digit? Be F plus F? F plus F is 30, right? 15 plus 15? Okay, how many times does 16 go into 30? Once. Doesn't quite go in twice, right? So it goes in once with what remainder? 15. F. Remainder of F. So overflow bit will always be a 0 or a 1 in hexadecimal math. Same thing true in decimal math. Have you ever carried something larger than a 1? Well, in hexadecimal math. Reminds me, there was some Facebook joke thing one time that was somebody filling out a McDonald's employment application. One of the questions on there was, can you carry at least 50 pounds? And then his answer was, of what? I thought that was funny. So answer is going to be what we're going to build up our answer in. Temp is what we're going to use to do our math each time. Walk from the end towards the beginning. Here we get our number, whatever overflow is, plus integer.parse into the first guy, integer.parse into the second guy, but we have an issue. We might do an integer.parse int of an F. Not going to cut it. So we're going to need to do a mapping here. So what we're going to need to make this all work is we can create a string. We'll call it map. And we want this guy to hold all of our hexadecimal digits. Now we'll just assume that you're going to enter in everything in uppercase, just for this example. So now what we're going to do is we are not just saying b.char at I. We're saying, in fact, we don't even need the parse int. So we're saying overflow plus map dot index of b1 dot char at I plus map dot index of b2 dot char at I. So if b1.char at I is a 3, let's say, where does 3 live in this string? It lives at position 3, the integer 3. Where does A live in this string? It lives at position 10, the integer 10. So these guys will be integers. Make sense? Then we'll take whatever our overflow is. Well, we'll set overflow equal to whatever temp is divided by 16. Then our answer is going to be temp times 16, but we need to reverse look that up in our map. So we're going to say map.char at that. So if our answer was supposed to be a 3, if temp mod 16 was a 3, char at 3, bucket 3, is the character 3. Char at bucket 10 is the character A. Char at bucket 15 is the character F. Make sense? All right, so that should do it for add hex. What was our sample we did over here? AB and 14. And this guy should give us a BF. There's our BF. And notice, because we made that decision, we're always tacking a 0 onto the front. If we wanted to fix that, we can just wrap this in a if. And say if overflow is greater than 0, then do this. And now it'll just be BF. So only tack the overflow on there if it made sense. All right, questions about that? So we see how those algorithms are identical. The reality is based on the current version of add hex, couldn't we take that guy, write a function called add base, have this guy take in a radix, and we'll just say it supports 0 to, well, we'll say it supports up to base 16 right now. And now we have a single method, add base, that will work for adding any bases together, because we have now written it generically. So this will work for all bases up to base 16. So I can call add base, passing it these two guys and a 16, and we get our answer. But I also add those in base 14, right? Different answer in base 14. $31 plus 212 is 243. Base 10 is 243. So we see how generic that algorithm is for adding things in any base. Now what's interesting with this is we just created an algorithm to add arbitrary size integers. We can do math in this that's bigger than the math we can do in Java. So for instance, if I say int a is equal to Let's just copy this. And we'll throw one more on there for good measure. This isn't going to work. The literal blue, blah, that whole big giant number that I can't read is out of range. Doesn't fit in an int. Ah, no problem. We'll just make it a long, right? Uh-oh. Doesn't fit in there either.
If you make a string and then you add the numbers, then have the toString method after you add them, would that work?
To make these guys a string.
If you change A into a string, and then you put parentheses around,
The double quotes around these guys.
yeah, no, parentheses. And then at the end you have the .toString method of that.
I mean, these are primitives. You can't call a toString method on that.
Well, then just plus the empty character. Would that work?
No, it'll turn it into a big long string. If I do plus the
No,
empty string like
end,
this.
You end the parentheses and then you plus it with the empty string.
like that,
Yeah, with that.
though it's still going to say these are out of range. It's treating this as math, and then this is concatenation.
Yeah. So it's okay.
It won't work. So hey, Java has that limitation, but you know what? Our algorithm we just wrote doesn't. We're going to steal this number, put it in here. We're going to steal this number, put it in here. That's in base 10. Let's comment out this broken line up here. And there's our answer. We just upgraded Java. There is a class Java object called big integer that supports arbitrary size integers. And one of its functions is a function called add. It takes another big integer as a parameter. We just essentially wrote whatever that guy has in it for add. And that wasn't that much code, is it? Add base, right here, the whole algorithm. We can add any bases now. We'll add to this subtraction after the midterm, blah, blah, blah. All right, any questions about the homework assignment? Any final questions about the exam? All right, I will see everybody on Thursday for the exam. Remember, if you're helping move, meet by the Circle Drive tomorrow at 4:30. And then Thursday, we got CS Get Together. Those are all our public service announcements.